We are going to talk a little bit about aqueous solutions, different types of solutions here. When we're going to take, first of all, we're going to talk about two specific definitions when we talk about solutions, and you should know both of these. All right. When we think of solutions, we usually think about solids in water, right? Like the copper 2 sulfate pentahydrate example that we did in class. That solid you measured out, you put it into water. So you think about the solute, otherwise known as a solid, in a solvent water. Okay. There's other kinds, and there's special names for those. For example, one that's pretty actually common is an alloy. Okay. So we need to know this definition here. An alloy is a solid solution of metals. An alloy is a solid solution of metals. Now you might say, well, what does that even mean? Well, they would usually take metals, of course, melt them down, mix them together, and let them basically cool down, re-solidify into their new, new structure, or new alloy, I guess you could say. If you add even just a small amount of one metal to a different metal, it takes on different properties. Okay? So when we think about things like, for example, bronze, you get a bronze medal at a hockey tournament or whatever the case might be. A bronze medal is made up of an alloy of copper and tin. So it's a mixture of copper and tin is what bronze is made out of. Alloys are, you've actually probably, if you're into cars at all, or motorcycles, or even bicycles for that matter, you hear about alloy frames, alloy wheels. What that means is that it's a mixture of metals. Okay? Usually aluminum, because aluminum doesn't tend to rust very well, or it doesn't rust, as well as some other things. So usually aluminum and sometimes magnesium for lightweight, strength, et cetera, et cetera. So that's what alloys are. Okay? Is a solid solution of metals. So once again, mixture. And it doesn't matter if you actually, and it does affect quite a bit. Just so you know, if you took like 75% magnesium and 25% aluminum, you would get very different structural properties than if you took vice versa kind of thing. So if you took 75% aluminum and 25% magnesium, you would get different strengths, et cetera, et cetera. So they play with all that stuff. They might add some stuff in to make it a little more durable and things like that. Okay. The second one you need to know is specific for mercury. So amalgams are solutions of mercury is the key there in other metals. Mercury is already a liquid at room temperature. So it's actually over there, Hg. Yeah, you know me. Hg is a liquid already. So they talk about a solid solution of mercury. Okay. They used to use amalgams, so mercury solutions like that. Obviously, combined with other metals gives you different properties, but they used to use that as cavity fillers, believe it or not. And then, guess what? That's not good, because mercury's poisonous. Yes? So they decided maybe that's not. Obviously, it wasn't completely mercury, but they might have had a little bit of mercury in there, and then realized that over time that's probably not such a good idea. Okay? Because mercury's poisonous, and that's obviously, I don't know what this has to do with it, but you know, the Mad Hatter, right? Same thing, because they used to have mercury-lined hats, right? And then these guys would wear those little bowling hats, and then they go a little crazy. Because mercury. Since mercury is a liquid at room temperature, an alloy of mercury and other metals is classified as a liquid in a solid solution, or what we call the amalgam. Okay. So just two definitions. You need to know those. Okay. We're going to talk a little bit about how things actually dissolve. Right. We're going to talk a little bit about the energy involved with that, and then we're going to refer to terms such as endothermic and exothermic. You know what? I think I'm going to skip most of this. I will talk about this, but I think I'm just going to show you some diagrams here as far as that goes. Let's get a bucket of water here. So, that's water. Water, remember, is polar. So, when we talk about water, we have a negative end and a positive end, yes, due to differences in electronegativity. All right. So if we had a solution of water, we would have, in this case here, hydrogen bonding. Yes, H bond to NO or F. Difference in electronegativity, bare positive nucleus, yada, yada, yada. And there would be a bond here, right? That's called hydrogen bonding, yes? Okay? Now, what happens when you actually put in some type of solid, whether it be sodium chloride or sugar molecule or whatever the case might be? Well, when you get some sodium chloride and you dump it into here, that's in solid form, of course. And when you dump it in, there's a process that happens, and it happens simultaneously. It happens very quickly, but we're going to break it down into sections just so you guys kind of understand all the things that are taking place. All at the same time, yes, but like I said, just to make it a little simpler. So when we dump this in here, we get sodium chloride, by the way, is very soluble. So we, of course, know that we get sodium ions and chloride ions, yes? Okay. How does that all take place? Well, there's three things that really need to take place for that to get that separated or get that dissolved into the solution. One of the first things that has to happen is when you first dump this in, initially you'd actually have sodium chloride solid probably, okay? So you would actually have that compound in solid form. This would be very, very quickly and initially. You would break what we call solvent-to-solvent bonds. So look, water is the solvent here, okay? It is what basically does the solution, yeah? So water is the solvent, and water, they're all connected together with these hydrogen bonds. We're going to break that bond. That's the first thing that has to happen. At the same time, we are going to break what we call solute to solute bonds. So what holds sodium chloride together? Well, in this term, it'd be ionic bonds. Okay? We're going to break, let's do this. We're going to break that bond, and we're going to break this bond here to give us those two ions. Okay? So we're going to break the solvent-to-solvent bond. That requires energy for that to do that. Now, in some cases, you may, and I'm not even talking about the heating it up on the stove, for example, or anything like that. There's chemical energy involved in that. It takes chemical energy to break that bond. Okay? It takes chemical energy to break this bond here, this sodium chloride bond, for example. So those are what we would call endothermic types of not really reactions, but endothermic types of heat. Okay? It requires energy. It takes energy in to break those apart. So water to water requires energy to break this bond, the hydrogen bond in that case there. Solid to solid has to be broken. Okay? That requires energy as well. Both of those we would consider endothermic. You're putting energy into that for that to happen. And finally, what happens at the end, okay, is that, I'm just going to actually move this here, probably the easiest thing to do, is that the sodium ion is attracted to, here, let me do this. The sodium ion is attracted to the positive part, and it forms an attraction there, okay? And the chloride ion is attracted to the negative part, the positive part of water. So the chloride ion might be attracted to, for example, the positive end of water. Okay? That step there releases energy. So when those reform together, and what we call that is the solvent, solute, okay? So we call that the solvent-to-solute bond. That releases energy. Okay? It depends on how much energy is required. Overall, we can talk about this as an endothermic or exothermic reaction. Okay? If it takes a lot of energy to break the solvent, and the solute-to-solute bonds, if it takes lots of energy to do that, we're putting a lot of endothermic in. We might not get a lot in exchange for that. So that solute-to-solvent bond might not give off a lot of energy. And in that case, this reaction would be endothermic, and I'll give you an example of that in a bit here. Okay. On the other hand, you might not have to put in a lot of energy. So you might not have to, maybe it doesn't take too much energy to break the water-to-water bond or the solute-to-solute bond, but it gives off a lot of energy at the end, okay, which would be an example of an exothermic reaction. All right? So kind of goes through this process here for you. There's, like I said, we've got two different examples here. We've got a molecular one. We've got an ionic one here. It doesn't matter, whichever. You've got water molecules here. Okay? The hydrogen bonds need to break, and ionic bonds need to break there as well. So the water bonds need to break. The ionic bonds need to break in that particular case there. So we would call this the solvent bonds, and we'd call this the solute bonds. Those both need to break. That's going to require energy. And then there will be some energy given off in the form of the solute to solvent bonds formed. So the sodium ion actually being attracted or attaching itself to a water molecule, and the chloride ion attaching itself to a water molecule as well. Okay. When a solute dissolves, this is the important stuff down here. Basically, we just need to kind of understand what's happening here. When a solute dissolves in a solvent, such as water, the three processes that are taking place there all occur simultaneously. Okay? The breaking of hydrogen ionic or intermolecular bonds is endothermic. So the solute to solute, the solvent to solvent is endothermic. The formation of the solute to solvent bonds is exothermic. And it just depends on which one is basically more. Does it require more energy to be put in than you get out? Well, that's endothermic. Or do you not put a lot of energy in, but you get a lot in return? That's exothermic. Okay? So that's what it talks about here, basically. It just talks about the fact that, once again, there's energy that's required to break bonds in the solute. If you added that to the energy required to break bonds in the solvent, and if you subtract from that the energy released from the bonds formed between the solute and solvent, that's your total energy change. And once again, if it's a positive value, it would be endothermic. So anything with a positive value there would be endothermic. Anything with a negative value would be exothermic. Anything with endothermic, like I said, positive value means you had to put a lot of energy in, and the result was you didn't get a lot of energy out. So endothermic. And if you ended up with a negative value, it'd be exothermic. Okay? To simplify that, or to kind of summarize that, you really should know these two things here. Okay? If the amount of energy required to break the bonds is more than the amount of energy released, then of course it's endothermic. And if you get a lot of energy released, and you didn't have to put much in, then it's exothermic. All right. Two examples of this are right here exactly. And in fact, we'll do one of these probably here. Dissolving sodium hydroxide in water. Sodium hydroxide, if you ever do that, if you put a lot of sodium hydroxide into water, you will get, it becomes very hot. Okay? And it's not necessarily a reaction per se. It is just simply breaking those bonds apart, breaking the sodium ions apart from the hydroxide ions. It becomes very hot. In some cases, you may not even be able to hold on to that beaker anymore. It gets really hot. Temperature changes quite drastic. Okay, so that would be an example of an exothermic reaction. It is giving off heat. Where does that heat go? Well, it's transferred to the solution, transferred to the beaker, and you feel it as hot, right? Like, for example, a hot pack, you know, the hot shot that you put in your glove, that's a chemical reaction, right? Giving off heat, that's exothermic. You can feel that, it warms up, okay? Ammonium nitrate in water does the opposite. Turns out it needs a lot of energy to break those ions apart, so it takes energy in, which means it basically takes energy from its surroundings, which means it cools off, okay? That's like, for example, one of those cold packs that's used in sports. You know, you break them, and then you put them on, right, and they're pretty cold. If you ever broke one of those, there's tiny, tiny little pebbles in there, and they're all white. They're all ammonium nitrate pebbles. That's what they are in a solution. And when those two mix together, okay, it becomes very cold, of course. That's a cold pack. So that's an endothermic reaction. Okay, it takes energy in from the surroundings. Okay. So, two things there. Like I said, exothermic, endothermic, and just a little bit about how the bonds break there as well. Okay.